Picture this. You're floating in the deepest void of space, far beyond any star or galaxy. The universe stretches out around you, infinite, silent, and growing. Every second, the space between galaxies stretches just a little more. Distant stars fade into red-shifted ghosts, receding forever. We've been told this expansion will never stop, driven by a mysterious force called dark energy. It will keep accelerating until the cosmos ends in a cold, lonely heat death. Everything torn apart, frozen in eternal darkness. But what if that's not the full story? What if the universe's expansion isn't eternal, and we're only seeing shadows of the truth? Let's dive into one of the biggest mysteries in cosmology. Why does the universe keep expanding, and will it ever stop? First, how do we even know it's expanding at all? It started back in the 1920s with Edwin Hubble. He looked at distant galaxies and noticed something wild. Their light was stretched, redshifted. The farther away a galaxy, the more its light shifts toward the red end of the spectrum. This isn't because the galaxies are moving through space like cars on a highway. No, space itself is expanding, carrying galaxies along like dots on an inflating balloon. This redshift is our smoking gun. Telescopes like Hubble and now James Webb have captured deep fields, images peering billions of light years away, showing ancient galaxies racing apart. But that's not all. The strongest evidence comes from the cosmic microwave background, or CMB, the faint glow left over from the Big Bang itself. This radiation fills the entire universe, cooled by expansion over 13.8 billion years to just 2.7 degrees above absolute zero. Its tiny temperature fluctuations match exactly what we'd expect from an expanding universe stretching those early ripples. Then there are Type 1a supernovae, massive stellar explosions that act like cosmic standard candles because they all explode with nearly the same brightness. In the 1990s, astronomers measured these distant blasts and found they were dimmer than expected, meaning the universe had accelerated its expansion, pushed by something repulsive, dark energy. Projects like DESI map millions of galaxies, confirming the pattern. Baryon acoustic oscillations, frozen sound waves from the early universe, act as a cosmic ruler, showing consistent expansion. All this points to the same conclusion. The universe is expanding, and for the last few billion years, it's been speeding up. So why won't it stop? In the standard model, dark energy, about 68% of the universe, acts like a constant repulsive force, overpowering gravity. It keeps pushing forever, leading to endless expansion. But here's where it gets really interesting, and a bit unsettling. As of late 2025, cracks are appearing in this picture. New studies, including one from November analyzing supernova data with corrections for biases in their brightness, suggest the acceleration might have peaked and is now slowing down. Dark energy could be weakening over time, evolving, not constant. DESI's latest results hint at this too. The force driving expansion might be fading. If that's true, gravity could win back control. Expansion slows, stops, and maybe even reverses into a big crunch, where everything collapses back in on itself. Imagine that. Instead of eternal cold emptiness, a fiery end billions of years from now. But we're not there yet. These findings are hotly debated. Some say the supernova corrections are flawed, others point to lingering Hubble tension, where different measurements of the expansion rate don't agree. And here's the humbling part. Our knowledge is limited. We can't directly see dark energy or dark matter. They're inferred from gravity's effects. Dark matter, 27% of the universe, holds galaxies together, but we've never detected its particles despite decades of searches. We predict based on models, but observations are indirect. Telescopes peer across billions of light years, but dust, biases, and assumptions creep in. James Webb has spotted surprisingly mature early galaxies, challenging timelines. Vast cosmic voids, like the Boots void, a 330 million light-year bubble with almost nothing, remind us how much emptiness there is. What if dark energy isn't a thing, but our equations are wrong on huge scales? Alternatives like modified gravity or tired light, where light loses energy over distance, try to explain redshift without expansion, but they struggle with the full evidence. We know so little. Dark matter could be particles, or something exotic. Dark energy? Maybe vacuum energy or a dynamic field. Our tech, amazing as it is, relies on predictions and patterns, not direct touch. The universe is vast, ancient, and indifferent. We're tiny observers on a speck, piecing together clues from light that left stars billions of years ago. Is expansion eternal? Or will it halt, reverse, and crush us all? As 2025 ends, the answer is, we don't know. But that's what makes it thrilling. Upcoming missions like Euclid and Rubin Observatory might settle it, or reveal even bigger mysteries. The cosmos isn't done surprising us. And maybe that's the scariest, most beautiful part. What do you think? Endless growth or cosmic collapse? Drop your thoughts below.